All right, so the recording is on. Um, yeah, I don't know. I feel like probably not a lot of people are going to be joining us, but I feel like we should probably get started.
No problem.
All right, so you guys can already see my screen, so allow me to present you the
I
DDPG
can't see your
paper.
screen.
Oh, right. Give me 1 second. Can you see my screen now?
Yes.
All right, so let's get started. The DDPG paper is a very easy read, actually. I feel like there's some issues, some minor details that require some sort of digging into, but overall, I think it's a very simple paper. The tasks in question. Oh, by the way, I'm gonna share the slides right now. Uh, Actually, I'm gonna do one last effort to. I'm just gonna tell everyone we're having the meeting right now, in case.
Okay.
Hey, Ali, how's it going?
Hey, not too bad. How are you?
Pretty good. Uh, had a had a busy week.
Yeah, same here.
I'm just gonna send a message to the Slack channel. All right. Yeah. So we were just starting on the presentation on the DDPG paper, and I just shared the link in the Slack channel in case you want to have access to the PowerPoint, um, to the slides. But yeah, I was saying overall, it's a pretty simple paper. The tasks in question are the tasks with continuous action spaces. They're interested in solving physical control tasks such as locomotion or controlling human joints, all these kind of things, and they want to replicate the success of the DQN with Atari. And they mentioned that the classical DQN method don't work directly. The reason is that DQN cannot be straightforwardly applied to continuous action domains since it relies on finding an action that maximizes action value function, which in continuous value case require iterative optimization process at every step. So that's a quote from the paper, and what that means is in a continuous action domain, yeah, because continuous values are basically not enumerable. So there are not even numerable number of actions for you to test out. So there's no direct way for you to find the actions that maximizes action value function. Usually people do like some sort of approximation. For example, if you treat the action as if you parameterize the actions and then pass the action through the neural network and then optimizes over the actions, then you can maybe find an action with a pretty high action value function, but there's no guarantee that is the global optimal action that maximizes the action value function. They further pointed out that discretization of the action space does not solve the problem, also does not solve the problem, and it has many drawbacks. Most notably, the number of actions you can execute with discretization increases combinatorially or exponentially with the degrees of freedom. The more discretization that you do, the more actions you can do, and the number of actions blows up, which makes the traditional DQN approach very difficult to apply. Uh, Lastly, they're just talking about some sort of observation space where they say we're gonna uh, use the low dimension. They're going to run the experiments using low dimensional observation, for example, joint angles and direct pixel inputs. And the algorithm consists of two parts mainly. The first part is the critic loss. That's how you optimize it. It's standard. So this case is actually fairly straightforward. You're trying to maximize the difference between the old Q value and the new Q value. The old Q value meaning the QST AT minus YT. YT is the new value, which is the reward after executing AT plus the discount factor times the Q value function of ST plus 1 mu st plus 1, and then the mu is the actor, which maps the states to actions directly. And then the second part is the actor loss. So their objective is to maximize the Q function, essentially maximize the Q function. And then essentially you take the gradient with respect to the neural network parameter of the actor, and then you use a chain rule to go from here to here. And actually, this part is a little bit tricky, and I feel like in implementation, we will be able to really realize what this chain rule sort of means. Because if we just kind of look at this, this is saying the gradient of the action with respect to the Q values. I'm not exactly sure what that means. Like the second part is very straightforward. It's a neural network parameter, the gradient of the neural network parameter with respect to the action. That is very straightforward, but I'm not very sure how do you calculate this directly. On the other hand, this chain rule might be directly handled by the AutoGrad package, by the PyTorch. So maybe we don't even have to worry about that, but really we just have to worry about getting the loss function set up correctly, which apparently is usually the case. But we'll see more of that in the upcoming implementation weeks.
I think
Yeah, go ahead.
regarding the differentiation with respect to the action, since you can see that for nabla AQSA, like just after the straight border is S equals ST, right?
Uh-huh.
And A equals mu ST.
Uh-huh.
So the nabla A is actually nabla mu ST.
Oh, I see. Yes, you're right. You're right.
So I think they just do it to simplify the notation.
Mm-hmm. Yeah.
But basically, once we get the Q value from the critic network itself, its derivative will be multiplied by the derivative of the theta mu parameters of the policy itself. So
I see.
general right there. Just notation is quite confusing.
Yeah, it is a little confusing. I'll have to take a second look at that and keep that in mind during the implementation weeks. And then this is the actual algorithm. By the way, I really probably should present this like the in full screen, especially with the pseudocode. So it's where you have a target network. You initialize a critic network, an actor network, and then you create a target network from them, and then you initialize a replay buffer, and then this is kind of interesting. After you start running the episodes, you select an action based on the actor plus this calligraphy NT, which is some exploration noise, which we'll get into in the next slides or discussions. And then they store in the replay buffer, everything in the replay buffer, sample from it, update it according to the critic loss as well as the actor loss, and eventually they update the target network. Notably, the same way that soft actor critic do the updates. It's a soft update. So they're not doing the hard update as the DQN would have done. So this is just one of the ways for them to do the update gradually.
Are you talking about the target networks?
Yes, how you do the update. So notice they're using the parameter tau, which is the same way that you would do the update for the soft actor critic.
But DQN does not do that.
DQN does not do that. Yeah, DQN does a hard update, which case the tau equal to 1. It's like every 300 steps or so, they do a hard update. So DDPG does this soft update where they do this sort of slowly, incrementally, instead of one-shot update as the DQN would have done.
Okay, thanks.
Yeah, no problem. And since we read the paper, Implementation Matters, I've been sort of keeping my eyes on a lot of implementation details because I started to realize, well, more and more, I realize they're probably going to have a significant impact on the performances. And sometimes when you do the implementation, what you're going to realize is that without any of those components, your algorithm might not perform as well as a performance presented in the paper. So I highlighted a lot of things when I was reading, especially the purple lines are the lines that mentions the specific tricks. And then here I just put in the slides as a summary. So they use a replay buffer to help with the sample being sort of independent, but also help with the catastrophic forgetting problem. They also does this soft target updates, which may or may not help the problem. They also do bash normalization. And bash normalization, if we look at the paper, is a process that normalizes each dimension across the samples in a mini batch to have unit mean and variance. In addition, it maintains a running average of mean and variance used for normalization during testing. Oh, I see. This is just for testing. Right. It mainly just normalizes the dimension across the samples to have unit means and the variance, which again may or may not help with the performance. But since it's produced by this, since this is from a highly prestigious institution, I would imagine they have done experiments 1,000 times and determined this is one of the best techniques that they could use.
I think it might be related to the fact that at that time, 2015, the batch normalization was very popular and it was like way to go.
Oh, I see. You're probably right. Yeah.
That's a big question. What exactly are they normalizing? Is it the observation?
Yes, observation, because it's a mini batch, right? Mini batch, you get the observations. I wouldn't imagine they do anything else other than mini. Let's see. This technique, yeah, samples in a mini batch. Well, there could be multiple things in a sample, right? Like the reward.
Rewards also.
Yeah, I really don't know, but I'm not sure. But I think maybe batch normalization is usually used for whatever is passed to the neural network. So in this case, it would be observations, right?
I see.
Yeah, because you don't pass the rewards into the neural network, right?
Well, for the Q, yes, you do not pass.
Right. That's more of something that you use to optimize.
Makes sense.
And then when they generate the action, they also added a noise, and then they use this Orstang-Uhlenbeck process to generate the noise. But if you read it up, the OpenAI version, they actually suggest that the version without let me see.
With Gaussian noise, I think they're using.
Yes, exactly. They're using the Gaussian optimizer, Gaussian noise, and they suggest it works just as well. And from an implementation standpoint, the Gaussian noise is much simpler to implement as well. So if you look at their DDPG, well, I guess this could be one of the things we discussed during implementation weeks, but it doesn't hurt for us to bring it up right now. So if you read it up here and you search for noise, you notice that the authors of the original DDPG paper recommended time-correlated OU noise, but more recent results suggest that uncorrelated mean zero Gaussian noise works perfectly well. And they don't add a citation, which kind of drives me crazy here. It's like, where recent results?
Probably internal stuff at OpenAI.
Probably, but it's. I was talking to my advisor about this, and he told me that this is one of the problem with not peer-reviewed blog posts, because there are things like this that are not cited. But in any case, if you look at the implementation, it's extremely easy. From the implementation standpoint, it's literally just saying the action noise scale, some just a regularization term, times a random some noise sampled from the Gaussian distribution. So from the implementation standpoint, it's much simpler. However, if you want the UB sampling noise, I think minimal RL does that, but I couldn't see like a reference or figure out why the formula makes sense. So he causes Ornstein Uhlenbeck noise. And then when I was looking this up on Wikipedia, they're not exactly the same. I'm not sure if this is really that. So the closest thing that I found is this, where you have theta times mu minus xt, and then if you come back here, you have the theta times mu minus x previous times dt, which is this term, plus sigma times dwt. And then this part is the same, plus sigma times, but this part, I don't know where this part comes from. And it has the normal variables as well. And I was reading through the Ornstein Uhlenbeck Wikipedia page, as well as a lot of other materials. I could not see where this derivation comes from.
So DWT is the infinitesimal Gaussian noise. So I think it makes sense. The NP net normal is just one sample from a Gaussian process. Normal thing.
But where is the where is this defined? Where's the literature suggesting for this formula? You know, that's what I was curious about.
I think that's just kind of like, so the difference between, say, Ornstein-Uhlenbeck process to just adding uncorrelated Gaussian noise is that you keep a sort of running average of it. So that's what the self.t is increment plus the previous value. It's just a one-step average of the previous x pre.
Mm-hmm.
I'm not sure that would be more recommended than just doing a Gaussian uncorrelated noise.
Yeah, I feel like I have to look more into this, but this is time correlated, unlike the Gaussian noise, which is not correlated at all. So, and if you look at their implementation, how they implemented the actor loss, it's so simple. It's unbelievable. But this is also some of the thing that I was saying. Like, if you look at a paper, it almost seems all we have to do is to define the Q. That's all, because all of the differentiation with respect to the chain rule, it's handled under the hood by the AutoGrad from the auto differentiation library that is used internally in PyTorch. So that shouldn't be something that we worry about, and the implementation here sort of proves that as well. But yeah, so that's the Oh, right. And as far as so we briefly went through the noise generated for acceleration, and then a couple other techniques that are used are action repeats. So what they do is, where's the action repeats? Right. In order to make the problem approximately fully observable in high-dimensional environment, we use action repeats. For each time step of the agent, we step simulation 3 time steps, repeating the agent's action and the rendering each time. Thus, the observation reported to the agent contained 9 feature maps, the RGB of each of the 3 renderings, which allows the agent to infer velocities using difference between frames. I think like intuitively this makes sense because it's now using a recurrent neural network with long short-term memory. Therefore, the agent could not remember what was the frame previously, and does not have any idea of the velocity. So if you do tricks like this, it sort of at least has its theoretical capabilities for the agent to infer things like that. But yeah, that's interesting. That's like it's always when you have an intended purpose, it's always questionable of whether that intention is actually carried through by the neural network. And lastly, the last technique that they will use is to downsample the frames to 68 by 68 pixels, and convert to float points. Convert the 8-bit RGB values to floating points scaled to 0 to 1. And if you're using the RGB pixel inputs. So that's about it for the code level optimization use. And then, it turns out this is actually the original DPG, which suggests target network are crucial. It actually doesn't show the performance of DDPG. The actual performance of the DDPG is reported here. Is reported here. Here, the last 2 columns, these 2, are the performance of DDPG. And then here are the performance. The first 4 columns are the performance of the DDPG. The last 2 columns are from the DPG's performance. I don't know if I said that wrong. But yeah, these 4 are from this paper, the DDPG's result. And as you can see, DDPG outperforms DPG, basically. But it's kind of hard to read because it's not like a diagram, which is why I put the other pictures in there, because this did not immediately catch my attention. All right. Right. So if you'll notice here, low D means its input is from the low dimensional, using the low dimensional observation, and then pixel is saying they're using the pixels to train. And then CNTRL means this is the results from original DPG algorithm with replay buffer and batch normalization. But they don't really tell you what's the input, right? Oh well, but yeah, so that's about it for the paper presentation. Do you guys have any questions or comments?
Yes, so I have like one thing to note that, in my opinion, like the fact that we are using actually, the not only we are this it can be like the benefit of this algorithm is not only that it's continuous, but also, in my opinion, the fact that we are using policy that replace the argmax and the policy which is neural network. So I think the neural networks can do much better job on the argmax. That's really huge benefit, in my opinion. I don't know, what do you think?
There's no argmax. I'm not sure. What do you mean?
I'm over the DQN.
Oh, right. Yeah. Yeah, so definitely by using DDPG, you don't have to do argmax anymore. So that's a huge plus from the computational
Yeah,
standpoint. It's more of using the policy gradient rather than argmax. Right.
exactly, exactly. And also question regarding this soft updates, because the time is set to 0.99. So this is, I don't know, I don't have really experience with this soft updates, but it sounds like we almost, they are all almost identical, right?
To the as opposed to the hard update, you mean?
Yes, yeah,
Um, I, I would say they might be similar, but maybe one is better than the other or in certain circumstances. I haven't seen like a report saying the soft update is definitively better, but it just seems to be one of the things that they do. Like an interesting experiments if you want to conduct is to experiment with the soft update with the DQN, see if it improves the DQN's performance. Like if you look at the code, here we have the DQN's code, for example. And how we do the update is essentially after a certain frequency, we update the target network with the Q network's parameters. So that's sort of like every 300 time steps we update the target network. However, in the soft update is essentially this, right? So if you want, if you're interested, you can do like an experiment to say what is the difference between the soft update and the hard updates, just by modifying this script into here and compare their performance.
yes, yes. Good idea. Yeah.
Mm-hmm.
Uh,
Yeah, I mean, if
Also,
mhm.
uh,
Yeah, go ahead.
no, also another thing is that with this noise, right? Because we apply this Gaussian noise, for example, which is constant, right? We could also try to manipulate this noise like decay exploration.
Yes. So, I think in one of the implementations that I've seen, they have this decay parameter for the noise, which is not implemented in the DQN in the OpenAI's repository. But that's definitely something that could be possible. Like you could have a instead of a linear rate annealing, you can have a noise scale annealing to sort of gradually decrease its contribution, right?
Yeah.
Yeah. Let me think. What else? But yeah, all I have. Do you guys any other comments or questions?
I think after having worked on subtractor critique, this one should be easy peasy.
Yes, yes. Software actor critic is a complicated algorithm, I would say. Yeah, it has many working components and something that are not really obvious to see. Not very intuitive, let's put it that way.
But most of those components are actually based on the DDPG. So
Yeah, so I think it's a very good it's very good that we revisit DDPG. Not only it's a simple algorithm for everyone to implement, but also it has um, it serves as the foundation for a lot of the future algorithms. Right. So, do you guys have any other questions or comments? Because if not, I have something to mention about the PPO optimization tricks. Some interesting discovery. Okay. So, one thing that I realize is that now I'm very certain that the implementation matters repository actually has a bug. It's with the return. So
Return normalization.
yes. So let me see where it is. Right. Per our discussions before, we found that the implementation matters paper, they really don't reset the reward filter, right?
Yes.
Right. And so, let me see if I can find it. Okay, you know what? I'm just gonna search for it. Like if you see the reward filter, so here, so this is the implementation matters repository, and then you can see they create a reward filter and they create a state filter, and then when they reset the environment, they reset the state filter. However, they don't reset the reward filter. However, so they claim all of the optimization tricks are from the OpenAI baselines library, and here I find very similar things, except in this is the baselines, OpenAI baselines library, except in OpenAI baselines library, they actually reset the returns. So notably here. Here, when you initialize it, you set the returns to be this, and then when you reset it, it becomes this, right? And then
By default, the filter reset is suggested.
yes, exactly. So that would, which I don't know if that would significantly impact their results, but one of the things that I've discovered.
Nice.
And the other thing that I notice is that they, if you look at the OpenAI baselines library, another trick that they do is called the advantage normalization. So notice they're already doing the return and observation normalization, right? However, if you read it up, their implementation, they normalizes the advantage as well, which I can't seem to find where. Should be in runners. No? Right. So if you see their model, they do have an advantage equals advantage minus a mean divided by the standard deviation. So the advantage normalization is also part of the tricks, which they did not mention.
And they did not use either.
Beg your pardon?
They do not use it either, I think.
You mean the baselines didn't use it, or what do you mean?
No, the implementation matters paper. They
No.
do not use.
Yeah, no,
But
they didn't use advantage normalization. Actually, did they? I haven't checked. I just know they didn't mention it in the paper.
they do not use it.
Did you check?
Wait. Sorry. Let me check one more time.
Yeah. No, I'm also gonna check. Yeah, because it's like the KL target KL technique. They didn't mention in the paper, but it is used, I believe, in their algorithms.
Um, there seems to actually be one result for advantage normalization.
So they did use it.
I'm not sure they use it, but there is a function to do it.
Can you share your screen? What's the file?
It's in policy gradient agents, if I'm not mistaken. How do you do this again? There you are.
Oh
Oh,
man.
it's policy gradients steps.py. Here there is a function to normalize the advantages. But
Okay. So it might be the case that's one of the things that its result did not stand out, and they just didn't use it.
it's not called anywhere, according to GitHub anyway.
I'm gonna actually search it up in the repository to see if that's actually the case. So that's code for papers and search. Actually, it is maybe used. Let me see. So surrogate rewards function calls the advantage normalization, and surrogate rewards, it is used. I think so.
Those sneaky developers, sneaky authors.
Yeah, I don't know why they didn't mention it, but it's definitely one of the things that they used. So
I think
surrogate.
that was trying to highlight all the important implementations they skipped over some.
Yeah, I know. How ironic, right? It's like, yeah, it's implementation matters. Why don't you tear out? You should probably add all of these things that you said are important, right?
Okay, so it probably doesn't matter then, the advantage normalization.
Probably, yeah. But we should do it in a yeah.
Yes,
We should probably add it to our code anyway.
for completeness sake.
Mm-hmm. Yeah, so I would say as a side task for the upcoming weeks, I was thinking that we could, so instead of using whatever they have, we could try to use the, instead of using the custom env, we should probably try to use the vector normalized environment to replace the custom env because it's more up to date and more feature complete, I suppose. Like many things you could tune, I suppose. Um, let me see. Wait, what? Oh, I see. Okay, right.
Are you sure? Because I see you're currently viewing the back normalize of the baseline implementation.
Yes.
Is that one still like regularly updated?
Baseline, I believe, is still very frequently updated, right? The last update is 28 days ago.
Okay, it's negotiating.
Yeah, I would say even though stable baseline does a pretty good job, I think baseline is still, they still maintain it they still use a lot of effort to maintain it. But you do see some things that are kind of sketchy, like this 2 years ago hyperparameters. Like I don't know about that. What is this anyway? Huh. Benchmark result, yeah, whatever. Okay. But yeah. And I think that's present in stable baselines too, right? If you go to stable baselines, interestingly, I think stable baselines implemented SAC, but not baselines, right? Yeah, that's correct. That's interesting. Yeah, if you go to stable baselines common vector inv and then you find the vector normalize, it's similar things except a little more documented, which I don't know. In my opinion, sometimes it's not necessarily the best thing. Like some of these functions seem so redundant. Like why would you try to load or save the running average? But there's probably a reason for it.
Yes, in some environments, or should I say experiments, they dump the whole environment to load it back during test time or something like that.
The what?
They dump, as they will save the policies and critics' weights, they
Uh-huh.
also save the environment in that current state so they can load it back to probably debug it or.
I see, I see. I mean, it makes sense. I mean, it's so if you think about it, it's always easy to add more functionalities, but from a readability standpoint, or I don't know, like it's a lot of code for some functionalities that are rarely used. I don't know. It's definitely a good thing for big libraries like this, but for small libraries like us, where we want to make it as easy to read and easy to use as possible, it's probably something that we don't want to add. But we should probably use this as a basis.
Okay.
All right. So the other thing I also want to hear you guys' opinions is I was thinking how could we run like hundreds of experiments using the CleanRL library. If a simple, like for example, a trivial example would be hyperparameter search. Like if I have 500 combination of parameters, how would I run 500 experiments in parallel? Because one experiment takes one processes, one CPU cores. Even if you have the best computer, it's not likely you're going to have 400 cores at the same time.
I'm just going to mention that I work on the Microsoft Azure team, so I
Mm-hmm.
might be able to distribute some of these jobs as ACI or Azure Batch jobs. You would have to create a Docker image and then
Uh-huh.
define how you want to do the scaling.
Are you seeing I open up the page and just
Yeah, that's why I was like very surreptitiously
Uh-huh.
looking at you. That
I see. Wait, did you say you work at Azure or?
Yeah, I work at Microsoft's research group, so we have like a collaboration with the Azure ML team.
Uh-huh. I
And
see.
I have some credits I could use and maybe even distribute a little bit of.
Uh-huh. Yeah, because
in terms of tuning, you could do just grid search, or we could try something more more strategic, like agent optimization or something like this.
Yeah. Well, that's more of an example. Like, for example, if we were to try to figure out, what combination of techniques that works best, or just in general, when you deal with combination of things, it's not necessarily like hyperparameters, but when those situation happens, you really need to run hundreds of experiments at the same time.
Yeah.
By the way, the reason why I mention it is so a lot of other companies, such as Google or AWS, they have similar services, but one thing they lack is the GPU Docker instance, which appears to be something that only Microsoft supports. So AWS they have something called Fargate, and if you look up their pricing, yeah, they don't have GPUs, right? Yeah, there's no GPU support. It is a little cheaper, but I think Azure probably has more potential, especially since it supports GPU. In any case, though, I think what would be something that might be possible with CleanRL running 500 hundreds of experiments at the same time is to use some services like that, because we don't have to buy a server of top-notch configuration, which takes a lot of money. This is more ephemeral instances that once you finish your job, they finish. By the way, Ali just sent an alternative. Let's check it out.
Yeah, so this is one way of doing containerized jobs that support both GPU and CPU workloads. And one nice thing about this is you can use, with Azure Batch, you can use low priority machines, which are kind of like spot VMs in AWS, are basically the unused capacity in the cluster or in the data center.
Oh, okay.
And they're set 5% off usually.
Wait, so I heard about these kind of instances. So do they? So if I understand that if they have like leftover computational power, they'll give it to you. But what if they don't have leftover? Do they just halt your program, or do they sort of lower the resources, give it to you?
No, so you can make a pool that is a combination of dedicated machines and low priority machines. The low priority machines you will be removed from the pool if the demand increases.
Okay.
So your job could potentially halt early if the demand shoots up.
Right.
Usually when I do these jobs, I do like 90% low priority and then 10% dedicated. That way, at least some of the jobs won't be killed.
But in a case of our experiments, I'm not sure whether this would be a good fit, because what if you're running experiments and then it just kind of cut off, and if you want to add something like a stop and resume functionality, it's gonna take a lot of code changes.
Well, I guess one thing you could do is save the checkpoints frequently, and then if your job is terminated, you can resume from the last checkpoint.
Okay.
Obviously, you can use the replay buffer or something like that, unless that's also checkpointed. But
right.
They're usually cheaper than using like Azure container instances or having a dedicated server, obviously. But yeah, there's that trade-off that you could potentially be kicked out of the
right
machine.
I see.
That being said, I've never been kicked out, but it could happen. I don't run really, really large jobs either. So
you have never personally encountered something like that?
No, I have not. So I often run jobs for scaling up simulators. Like if I want to run 100 simulators at a time for a very slow simulator, then I use Azure Batch, and I often do like 90% low priority, 10% dedicated, and I have never had my low priority pool downsized or removed.
Oh, really? Yeah, I would be okay with downsizing, but removed might be a little difficult to handle. But yeah, I think that will be something worth looking into. Because if I take a pretty quick calculation, if we do this without a GPU, how much would that be? Let me think. Do a quick calculation on the fly here. So assuming I want 1 gigabyte of memory, which is probably enough to run Python scripts. Actually, probably need 2. And then I probably only need 1 course.
You say memory. The replay buffer can grow quite big in some experiments.
Yes, so that's more of a variable. So if I have 500 experiments and then 4 hours each of them, really? That doesn't seem very likely. Oh, sorry, that's second. Right. So, right. So times 60 is an hour, times 500.
It should be a minute, I guess, if it's second.
Oh, yes. That's only a minute, and then so times another 60 for the hour, and then times 4 hours. That still doesn't look right? Is that too cheap?
I guess.
It's a pretty small machine, only have one CPU, so
You left the 500 somewhere.
Oh, yes, right. Right. But
$10, I guess.
okay, $100 for 500 experiments in 4 hours.
Thanks, but no thanks.
Yeah, I guess. Yeah.
Shipyard or Azure?
Huh? Beg your
It's
pardon?
Azure. Right?
Yeah, it's
It's
Azure.
Yeah.
Yeah, with AWS per instance, it's probably going to be cheaper, but yeah, it still seems a little bit expensive. But maybe with the batch shipyard, it's probably going to get a lot cheaper. Do you know how much cheaper? I think with AWS, it's like 75% cheaper. So if
Yeah, spot instances are usually 75% cheaper, but you're comparing not a VM to Azure Batch, but a container from Azure Container Instances.
it will be a what?
So, yeah, so usually it's 75% cheaper, if I remember correctly. It does vary from region to region and by machine type.
Right.
So you can basically divide your cost by 4. But you weren't comparing a VM. The first calculation was for Azure Container Instances, right? Yeah, that's not exactly a VM price. That's like a container price. So I'm not.
Right. Is batch shipyard a container, an equivalent to container instance service, or is it more like to a VM instance service?
It's more like a pool of VM instances.
Oh, okay. Never mind. Then it's a little bit different.
You can run containers as a workload on those VMs, and Batch Shipyard makes it really easy to do that.
Okay.
But the pricing is going to be a little different. Like you're not comparing.
Right. Because you're having VMs, right?
Yeah.
Huh. Interesting. I wonder. Yeah, I'm probably gonna look it up this and see if they have a price calculator to make it reasonable or something like that. But yeah, exciting stuff. At least, yeah. At least if we at least we know if we built some containers like that, we know we would have the capacity to basically run a lot of things at the same time. It would be like something theoretical that we can do, I guess. Oh wow! So there's like a discount. It's pretty interesting.
Yeah, at the top of that page, will show you the drop down for right now standard priority. But if you click the low priority, the cheaper. And then it tells you which region is cheapest. So the best region for that machine type is East US.
I probably need some time to do the sorting, right? Like I see some 30% off or whatever, but it's not refreshing.
It's annoying.
Yeah, it's okay though. Well, thanks so much for letting me know this. I'll definitely evaluate a lot of the possibilities and see which one will be suited for running large-scale experiments. Because I feel like you have two kinds of large-scale experiments. One is sort of you're running you're running a lot of experiments to see which is better versus running one experiment with a lot of neural network parameters and just for that particular instance, if that makes sense. like training an instance for StarCraft 2 would be an example. It takes a lot of computational power for even a single agent, right?
Yeah.
But yeah, this is good. Thanks everyone for the good work. And if you guys have a chance, please try to do the implementation before next Friday so that we can compare our codes. And in the meantime, if you have any questions, please post it in the Slack channel and then we can talk about it. Yeah, exciting. Really looking forward toward this.
Yeah, thank you.
Yeah, thank you. Anyone have last minute questions or comments? All right.
I have a question.
Yeah, go ahead.
Have you experimented with parameter space noise?
I saw that paper actually because of the DDPG paper. That seems to be a different thing compared to the UG noise that was mentioned in the DDPG paper, though.
You mean OU, right?
Hmm?
You mean OU?
Yes.
Ornstein
Oh, yeah.
overlap?
Yeah. Yes.
Actually, I did some experiments and it does not seem to change much.
Really? Yeah, it's one of the things, right? Oh, are you having some experiments to show already? Yeah, Rosalind is a little ahead of us. He's already implemented a bunch of things with DDPG apparently.
Sorry for that.
It's okay. It's okay. That's perfectly fine.
I'm not sure the code was actually clean enough, but I tried with the OU, the naive.
Uh-huh.
This is probably not normal uh, action noising and also the parameter one. But
Uh-huh.
this one is actually really naive. I basically just add some
Okay.
noise standard deviation to the neural network weights themselves.
Uh-huh.
I did
Yes.
not make the paper, so that's the intuition. But it kind of seems to work. In this case, the parameter noise is the one in purple.
Mm-hmm.
Especially in half bullet, it actually gets the highest performance.
Oh, really? Wow.
But we still have to see because the other two are still running. So
I see. That's pretty interesting. Yeah.
I wonder.
Yeah, I'll definitely. Yeah, that will definitely be something that I'll look into when we do the implementation. And I'll be very exciting to see how would we code up things differently this time.
In any case, Gaussian noise seems quite enough already.
Yeah. If anything, if Gaussian noise is good enough, I don't see any reason why would we go for the more complicated things because then those techniques will not be justifiable. You know, they're more complex and they don't do too much.
One more thing that kind of grinds my gear is that in the papers, usually they have quite a pretty curves, right?
Uh-huh.
Show the performance at the end, but no matter how hard I try, I usually have that kind of mountains.
Yeah, that is kind of interesting, right? You have some really good. It almost sounds like, yeah. I think something you might be interested in doing is try to print out the logits. I wonder if the logits will kind of explode, like in other experiments where we don't have the KL boundness.
There's also the problem of deterministic evaluation. I think in this case, it's the result, the returns of the agent while we're still adding some noise to the actions.
Mm-hmm.
The optimal policy should be the one which is, sampled without the noise, right?
Mm-hmm.
So I think it might be useful or relevant to include it in the further implementations.
Right. So I personally find the difference between the evaluation and training to be kind of trivial, and I feel like it adds a lot of complexity to the code because you're maintaining two sets of statistics, and then you're running the environments in different ways, and their performances are usually very the difference between their performance are very little, you know.
Yes,
Yeah.
it's true.
Yeah, that's why I don't see there's a huge like it makes sense, like, because if you evaluate it, if you do it